So we are further proceeding with the communication system, and now our special discussion is regarding the space wave propagation. Space wave means we are referring to radio wave or the carrier wave propagation in the space. The space wave propagation is important for the astronauts or for the different celestial bodies. If a satellite is in the space, or if the astronauts are in the space, or astronauts are on the surface of Moon or the Mars, then we have to carry out the space wave propagation. The space wave is related to the electromagnetic wave or the radio wave communication. As I have suggested, electromagnetic wave has got a spectrum, and there are various members of the spectrum. Like, for example, the radio waves are used for radio communication. Second member is infrared. It produces slight heat. So during the landing of aeroplanes, it is giving rise to slightly high temperature, and fog can be removed. And number three is the visible light, and it is used for carrying out the photoelectric emission, specifically in alkali metals. However, exception is francium because it is already radioactive. Then the fourth member is ultraviolet radiation, and they exhibit photoelectric emission in about 90% of cases. And then comes X-rays, which are used in radiography and radiotherapy. Then finally we come to gamma rays, and that is used for cancer therapy, and that is taken from cobalt-60 isotope. So these are various members of the electromagnetic spectrum. However, we have to limit our knowledge to only space wave propagation, that is only radio wave propagation. So we have to go through with the factors which limit its range of propagation. So what is the space wave propagation? The television frequencies lie in the range 100 to 220 megahertz. In this transmission, the reception is possible only if the receiving antenna directly intercepts the signal. If a radio wave transmitted from an antenna traveling in a straight line directly reaches the receiving antenna, it is called a space wave. So space wave is nothing, it is directly coming to the antenna. The space wave propagation is also called the tropospheric or a line of sight propagation. Tropospheric means which are communicated from in 12 kilometers from the sea level. It depends upon if the frequency is more, we can carry out right up to the very far off space, but otherwise tropospheric space. The tropospheric space is about 0 to 12 kilometers from the sea level. The range of space wave propagation is limited by the line of sight distance, that is distance at which the transmitting and receiving antenna can see each other. The curvature of Earth is also involved in this. So on the curvature of Earth, we will just adjust the antenna and they will be in the line of sight. Now we have to deduce an expression for the distance up to which the TV signals can directly be received from TV tower of height h. So a figure is made here. The range of the transmitting antenna, that is TV signals, be transmitted from antenna of height PQ, that is HT. Due to curvature of the Earth, no direct signals are possible beyond the point S. So point S is indicated, and point S or T. That is one of the extreme points of the curvature as shown in the figure. So the long tower is indicating antenna or antenna tower, and P is a point, up to Q it is the antenna tower, and communication is possible within the range of S and T. R is the radius and O is the other extreme point. Now geometrically we have to go through from the figure, that is PS is equal to PT is equal to D. So look at, check the figure, PS is equal to PT. So curvatures are equal, and that is equal to D. Now from right angle triangle OTQ, now check up O, T and Q, that is the right angle triangle. We get OQ square, that is we have to use the Pythagoras theorem. that is the hypotenuse square is equal to square of the other two sides. So OQ square will be equal to OT square plus QT square. Here we have used the Pythagoras theorem. Here, now we take the square root. So first of all, OT is kept equal to R. So now check up the figure and see OT. The OT is marked with a dotted line and it is equal to R. Similarly, from O to P, it is again R. So OT square is replaced by R and HT, that is replacing QT square. So QT will be equal to PT equal to D, as it is given right in the first line. OT is equal to R, that is the radius of Earth. So R plus HT whole square will be equal to how much? We will open up the square, that is R square plus H square HT square plus 2RHT. So from that we will compute these values and that will become equal to R square plus D square. Now R square plus HT square plus 2HTR, as I have suggested, equal to R square plus D square. From both sides, R square will cancel off and we will make the subject of equation D square. So D square will be calculated by function HT square plus 2HT into R equal to 2HTR. That is, we have taken out 2HTR common and divided the inner portion. So it will become 1 plus HT over 2R. HT is very, very less than R. Therefore, D square is equal to 2HTR because HT is negligible. And D will be calculated by under root of 2HTR. Now our next question, that is expression for the maximum line of sight. LOS stands for the line of sight, distance between the two antennas for the space wave propagation. So we are seeing the figure here, that is the antenna is fixed on the curvature at the two extremes and they are in the line of sight. That is transmitting antenna and the receiving antenna, they are in the line of sight. So there is a direct path. So all the different parameters are mentioned and now this range of space wave propagation between the two antenna on the Earth's surface, how to carry it out. A space wave travels in a straight line from transmitting antenna to the receiving antenna. That is, it is a line of sight communication. Due to curvature of the Earth, direct space waves get blocked at some points. Thus, the Earth presents a horizon to space wave propagation, commonly called radio horizon. Now, the figure shows the effect of antenna height on the radio horizon. The line of sight radio horizon for a single antenna at C is given by D is equal to under root 2RH, where R stands for the radius and H stands for the height. D distance to the radio horizon, H antenna height above the sea level, and R is the radius of Earth. The maximum line of sight, that is distance dn. So maximum line of sight, that is distance dn between the transmitting and receiving antenna is given by dm is equal to dt plus dr. So for dt and dr we compute the values and those values are 2rht under root plus 2rhr. We can take out common as root 2r and within the bracket we can write that is square root of ht plus square root of hr. Now dt is the radio horizon for transmitting antenna, dr is the radio horizon for receiving antenna, ht is the height of the transmitting antenna and hr is the height of the receiving antenna. Clearly, if the signal is to be received beyond the horizon, then the height of the receiving antenna must be large enough so as to intercept the line of sight wave directly. Moreover, the power transmitted from transmitter decreases nearly as the inverse square of the distance. So power is again following the inverse square law, that is, if distance is more, power loss will be more, and if distance is less, the power loss will be less. So effective power transmission will be possible when the two parts are quite close to each other. quite close does not mean that they are just only 1 kilometer apart. So the signal becomes weaker with the increasing distance. Hence, the range of TV transmission can be increased by increasing the height of the transmitting and receiving antennas. Maximum they can go up to 300 meters by using the repeater transmitting stations.